I'm going to solve problem number 4. Problem number 4 says that propine, C3H4, undergoes combustion with oxygen, Brinkelhoff, to produce carbon dioxide and water. It wants us to balance this. I think, let's try 3 carbons. So that's, carbons are 3, carbons are 3, H's are 4, H's are 2, oxygens are 2, oxygens are 6, 7 now, okay? Let's see, let's double the hydrogens on this side. That'll make 4. And that is going to make this 8 oxygens. So we need to put a 4 here to make 8 oxygens. So we have a balanced chemical reaction. Next, I'm going to see what the problem asks. We have 52.0 liters of propine. So I'm going to rewrite the balanced equation here. So 52.0 liters of propine at 1.24 atmosphere and 2870 degrees Celsius. And we want to find out what volume and mass of oxygen is required. So we want volume and mass of oxygen is required, and then they're going to ask us for, I think, carbon dioxide and water. Both liters and grams, both liters and grams. So, first of all, the only way I can do these mole conversions is if I have moles. And if you notice, all of these can be plugged into PV equals nRT to get moles. So, let's see here. We've got N equals PV over RT, which is equal to the pressure of 1.24 atmosphere, volume 52.0 liters. Notice this is to figure out the number of moles of propine. Divided by R, 0.0821 liters atmosphere per k mole, times temperature, which is 2870 plus 273.15 to get Kelvin. Let's see if I have a calculator. Hold on one second. Grabbing a calculator, I'm going to put these numbers in here. 1.24 times 52 divided by 0.0821 divided by 2870 plus 273.15, and I get 0.250 moles. Remember, that's of propine, 0.250 moles. So I have 0.250 moles of propine. That's a 1:4 ratio with oxygen. So that means I'm going to need 4 times as many moles of oxygen. So that's going to be 1 mole of oxygen. That's going to produce 3 moles of carbon dioxide. If we start off with 0.25 moles, which is a 1:3 ratio, I'm going to make 3 times that, which is 0.750 mole. And for water, I'm going to make 2 times that. 2 times that mole is 0.500 mole. Once I know how many moles I'm going to make of oxygen, or require of oxygen, and make of carbon dioxide, and make of water, I can convert them to grams by multiplying by the molar mass, and or convert them to liters by using PV equals nRT. The reason we need to use the ideal gas law is because we're not at standard temperature and pressure. So let's start with oxygen, okay? To figure out the number of liters of oxygen, I'm going to have to use V equals nRT over P. Let me figure out what the temperature is, first of all. It's 2870 plus 273.15, and that's 3143.15. Okay, so the volume is the number of moles of oxygen, in this case, because we're finding the volume of oxygen. So that's 1.0, probably 1.00 mole of oxygen times Rydberg's constant times temperature, which is 3143.15 Kelvin, all over pressure, which is, we're in the same container, so the pressure is the same. So we have 1 times 0.0821 times 3143.15 divided by 1.24, and we get 208 in 3 sig figs, so it's 208 liters. To get grams of oxygen, how many grams of oxygen is equal to 1.00 mole of oxygen? To cancel out moles of oxygen, we know that 1 mole of oxygen is equal to 32.00 grams. So we produce 32.0 grams of oxygen in 3 sig figs. So that's oxygen. Now we do the same thing with carbon dioxide. Carbon dioxide, we're going to have 0.750 moles, and for water, we're going to have 0.500 moles. Okay, so carbon dioxide, we want to do liters. So liters we're going to get from B equals nRT over P. And for grams, we're going to use the molar mass. So remember, the number of moles of carbon dioxide is 0.750 mole times Rydberg's constant times temperature, 3143.15 Kelvin, divided by pressure, 1.24 atmosphere. We plug those numbers into our calculator. We've got 0.75 times 0.0821 times 3143.15 divided by 1.24, and we get 156 liters. For grams, how many grams of carbon dioxide is equal to 0.750 mole of carbon dioxide? We know that 1 mole of carbon dioxide is, I think, 44.01 grams of carbon dioxide. We do that math, 0.75 times 44.01, and we have 33.0 grams of carbon dioxide. By the way, this is carbon dioxide too. 33.0 grams of carbon dioxide. We then can do the same thing for water. Remember, on our previous page, water has 2 times the number of moles of propine. Propine is, here we are, propine is 0.25 moles, so 2 times that is going to be 0.500 moles of water. So V equals nRT over P, which is the number of moles of water, which is a half a mole, times Rydberg's constant, times temperature, all over pressure, 1.24 atmosphere. And plugging that in, 0.5 times 0.0821 times 3143.15 divided by 1.24 gives us 104 liters of water vapor. And then grams, how many grams H2O is equal to 0.500 moles of H2O? We know that the molar mass of H2O is about 18 grams, so 1 mole of H2O. So half of that is going to be, it's going to work out to be about 9 grams. But let's put this in. It's 18.016, I think, grams per mole. 18.016 times 0.5 is 9.008. So 9.0, let's look at that again. 9.008 in 3 sig figs is going to be 9.01 grams. And that is our problem, 9.01 grams of H2O. So So the trick with these is just figuring out what the moles of all of these are and then plugging them into the equation. Let me show you one other neat little thing, is that because the volume has nothing to do with the type of gas it is, just with the number of moles of gas, we didn't need to do PV equals nRT all the way through. Let me show you. If 1 mole of gas had a volume of 52 liters, then 4 times that should have 4 times that volume. 4 times that has 4 times, so I'm trying to do this with the video here. So if we go to C3H4 plus 4O2 yields 3CO2 plus 2H2O. Since volume is strictly based on molar ratio, not on the identity of the gas, unlike molar mass, if I know if these are all at the same conditions of temperature and pressure, if this is 52.0 liters, then that's going to react with 4 times 52.0 liters to make 3 times 52.0 liters, because this is a molar ratio of 1 to 4 to 3, plus 2 times 52.0 liters of water. 4 times 52 is, it's like 208 liters. 3 times 52 is 156 liters, I think. And 2 times 52 is 104 liters. So that part was actually really easy once we figured out the moles. And so we didn't have to do PV equals nRT all that time. We just needed to figure out that ratio. And then we did need the moles again to calculate the molar mass. And then you need the identity of the molecule to figure out how many grams.